Most genetic mutations are inconvenient at best and lethal at worst. But every so often, the DNA dice land in a way that quietly hands someone a superpower. Better eyes, denser bones, immunity to a virus that has killed millions of other people. These are not comic book powers. They are real biological tweaks that exist in living humans right now, sometimes documented in only a handful of confirmed cases, sometimes scattered across entire populations who never realized they were operating on different hardware than everyone else. Here are the 12 most fascinating real-world genetic mutations that grant humans something approaching a superpower, ranked by utility. Starting with sensory upgrades that change how you perceive the world, and ending with mutations that flat out extend how long you stay in it. Tetrachromacy. Most humans see the world in roughly 1 million colors, give or take, using 3 types of cone cells in the retina that handle red, green, and blue wavelengths. Tetrachromats have 4. They are operating with an entire extra channel of color information that the rest of us simply do not have. The mutation responsible is X-linked, which is why functional tetrachromacy is almost exclusively found in women. They have 2 X chromosomes, giving them 2 chances to inherit a slightly shifted variant of the red or green cone gene. When both versions express together, the result is an extra cone type that picks up wavelengths the standard 3 cones blur over. Estimates suggest some tetrachromats can distinguish around 100 million colors, which is roughly a 100-fold increase over the human baseline. The biological trade-off is small but real. The brain has to process more channels of input, and not everyone who is genetically tetrachromatic is actually functionally tetrachromatic. Many carry the genes without ever consciously experiencing the extra range, because the brain only develops the wiring to interpret the 4th channel if it gets trained early enough. The extraordinary benefit for the ones who do develop it is a richer perceptual world, distinctions in paint colors, in flower petals, in skin tones, in produce ripeness, that most people will never see no matter how long they look. The rarity is the sticking point. Genetic tetrachromacy might appear in around 12% of women, but functional, behaviorally confirmed tetrachromacy is far rarer. Only a handful of cases have been verified in lab settings worldwide. MSSP. A small number of people remember everything, not in the figurative sense, in the literal no detail is too small sense. Ask them what they had for breakfast on a Tuesday in 2003, and they can tell you, plus the weather, plus what they were wearing, plus a song they heard in passing on the radio that afternoon. The cluster of genetic and neural factors involved in this trait, including markers researchers have grouped under labels like MSSP, appears to involve enhanced connectivity between the hippocampus, the temporal lobes, and the regions responsible for autobiographical narrative. The brain simply refuses to throw memories away the way ordinary brains do. Most people forget by design. These brains do not have the off switch. The biological trade-off is significant and surprisingly heavy. People with this trait describe it less as a gift and more as a low-grade burden. Painful memories never fade. Old embarrassments stay sharp decades later. The mental clutter of remembering every minor disappointment in high definition makes letting go nearly impossible, and several confirmed cases have reported anxiety and depression linked specifically to the inability to forget. The benefit in daily life is enormous when it gets pointed at the right targets. Perfect recall of conversations, faces, addresses, deadlines, and personal history without any external aid. It is a permanent advantage in any field that rewards memorization, from law to medicine to academic research. The rarity is extreme. Fewer than 100 confirmed cases of true MSSP-level autobiographical memory exist in the published literature, making this one of the rarest cognitive variations on the list. DC2 mutation. Most adults need 7 to 9 hours of sleep to function. People with a mutation in the DEC2 gene, also written as BHLHE41, need 4 to 6, and report feeling completely rested, energized, and cognitively normal the entire next day. They are not sleep deprived. Their bodies have simply rewritten the contract on how much rest a human requires to operate. The mutation alters how the brain regulates the sleep-wake cycle, compressing the restorative functions of deep sleep into a shorter window. Where a standard sleeper needs 8 hours to cycle through all the necessary maintenance, memory consolidation, hormone regulation, cellular cleanup, a DEC2 carrier hits all the same biological checkpoints in 5. The biological trade-off is surprisingly small. Researchers studying confirmed cases have not found significant negative health outcomes. If anything, short sleepers tend to be high functioning, energetic, and resistant to mood disorders. The benefit is roughly 2 to 4 extra waking hours per day, every single day, for life. Over a 70-year span, a DEC2 carrier gets the equivalent of more than a decade of additional conscious time compared to a standard sleeper. The rarity is significant. Confirmed DEC2 mutations are estimated to appear in less than 1% of the population, and many people who think they are short sleepers are actually just chronically under-rested. True genetic short sleeping has been verified in only a handful of families, traced through multiple generations. DEC2, the same DEC2 gene family that produces short sleepers, also influences broader fatigue resistance, the ability to push through long periods of mental and physical exertion without the standard human energy crash. Researchers sometimes refer to the broader human variant as HDEC2, and the phenotype goes beyond just needing less sleep. These people seem to operate on a flatter, more sustained energy curve, where most people have predictable afternoon slumps, post-exertion exhaustion, and a hard ceiling on how many consecutive hours they can stay sharp. HDEC2 carriers report fewer of these crashes. They recover faster between physical demands, sustain mental focus longer in single sessions, and seem less affected by the cumulative fatigue of multi-day stress. The biological trade-off is mostly an open research question. Long-term data is still limited, but some studies suggest that the constant low fatigue state might mask the early warning signs the body normally uses to signal overexertion. If your body never says, "I am tired," you might push past limits you should have respected and only find out about the damage afterward. The benefit, especially in demanding careers, surgeons, military operators, founders running on fumes for months at a time, is the difference between burning out at 40 and operating at full capacity at 60. The rarity is on par with the short sleeper variant. The two phenotypes overlap heavily, and together they account for a tiny percentage of the overall population. ACTN3. The ACTN3 gene codes for alpha-actinin 3, a protein found in fast-twitch muscle fibers, the explosive ones that fire for sprints, jumps, and short bursts of maximum effort. About 18% of people carry two non-functional copies of ACTN3, meaning they produce no alpha-actinin 3 at all and rely on slower twitch substitutes. The other 82% have at least one working copy, and the elite sprinter population is dominated by people with two. Studies of Olympic sprinters have found that the active version of ACTN3 is essentially universal among world-class sprint athletes. The protein allows fast twitch fibers to contract harder and faster, transferring more force into the ground in the fraction of a second a sprint stride takes. The biological trade-off is real and slightly funny. The same mutation that makes you a great sprinter makes you a worse endurance athlete. The non-functional ACTN3 variant is actually more common in elite long-distance runners, because slower twitch dominance favors aerobic efficiency. You can be wired for speed or wired for distance, but biology generally makes you choose one. The benefit is explosive athletic power, faster reaction times in short bursts, and a meaningful edge in any sport that rewards acceleration. The rarity is the lowest on this list. The active variant is the default for most people, but the specific double active configuration found in elite sprinters skews more toward 30% of the population, and the genetic odds still stack against you at the truly world-class level. EPAS-1. At 14,000 feet of elevation, most humans struggle to breathe. Tibetans live there full-time, run, work, and raise families with no apparent issue. The reason is a mutation in EPAS-1, a gene that regulates how the body responds to low oxygen, and the version Tibetans carry is one of the strongest natural selection signals in recent human evolution. The mutation rewrites the body's hypoxia response. Most people in low oxygen environments react by producing more red blood cells to carry more oxygen, which works short-term but thickens the blood, raises blood pressure, and causes long-term altitude sickness. EPAS-1 carriers do not do this. They use the oxygen they have more efficiently at the cellular level, getting more work out of less air without the blood thickening that hurts everyone else. The biological trade-off is essentially nothing at altitude, and at sea level the mutation is mostly neutral. The benefit is enormous in any low-oxygen environment: mountaineering, high-altitude athletics, certain professions involving thin air. Tibetan endurance at elevation is not a result of training. It is hardware. The rarity is interesting because the mutation came from interbreeding with Denisovans, an extinct human cousin, tens of thousands of years ago. The EPAS1 variant is common across Tibetan populations and rare everywhere else, making it one of the few confirmed cases of an extinct hominin gene quietly giving modern humans a measurable edge over their neighbors. Myostatin-related muscle hypertrophy. Myostatin is the protein your body produces to tell muscles to stop growing. It is a built-in governor, present in every healthy human, capping skeletal muscle development at a level the body considers reasonable. Some people are born with a mutation that disables myostatin production entirely, and their muscles never get the stop signal. The result is dramatically increased muscle mass with very low body fat, often visible from birth. A famous documented case involves a child born in Germany with double the normal muscle mass for his age, capable of lifting weights as a toddler that healthy adults struggle with. The same mutation occurs naturally in Belgian blue cattle and in certain breeds of dog, producing the same hypertrophied look on a different species. The biological trade-off is poorly understood, partly because so few cases have been studied long-term. The mutation appears largely benign in childhood, but the long-term effects on heart muscle, tendon strength, and joint wear are open questions. Myostatin regulates more than just skeletal muscle, and bypassing it everywhere may have hidden costs the data has not caught up with yet. The benefit is straightforward: strength levels that would require years of dedicated training in someone with normal myostatin, available from birth, maintained with minimal effort. The rarity is extreme. Only a handful of confirmed human cases exist worldwide, making this one of the most genuinely unique mutations on the entire list. PCSK9 inhibition. The PCSK9 protein helps regulate how much LDL cholesterol, the bad kind, stays circulating in your blood. Some people are born with a loss-of-function mutation that essentially turns this regulator off, leaving their LDL levels permanently low, automatically with no diet or medication required. The first major study of these carriers found that they had around 88% lower risk of heart disease than the general population. The mutation has been studied intensely because it is basically a blueprint for a drug. Pharmaceutical companies have already developed PCSK9 inhibitors that mimic the effect, and they work, but the carriers get the effect for free for their entire lives, starting at conception. The biological trade-off appears minimal. Decades of research on PCSK9 loss-of-function carriers have failed to identify any meaningful downside. Cholesterol management is one of the rare cases where lower really does seem to be better. The benefit is a lifetime of cardiovascular protection without effort, without medication, without lifestyle compromise. Carriers can eat steak and ice cream, and their LDL stays low. The rarity varies by population. The most studied variants appear in about 2 to 3% of certain populations, including specific African American cohorts where the protective effect was first identified. Globally, true loss-of-function PCSK9 mutations are uncommon, but the population of people walking around with permanent metabolic armor against the leading cause of death in the world is larger than you might guess. LRP5 mutation. In 1994, a Connecticut man walked away from a serious car accident without a single broken bone. Doctors investigating his unusual skeletal density traced it back to a gain-of-function mutation in the LRP5 gene, which controls bone formation. His skeleton was, by ordinary standards, nearly unbreakable. The mutation cranks up bone-building signals far beyond normal levels. Carriers have bone density measurements off the standard medical scale, sometimes 2 or 3 times the density of normal adult bone. They report no history of fractures, even after injuries that would shatter typical skeletons. Their entire family line, tracked back through generations, shared the trait without ever realizing it was unusual. The biological trade-off is, in this case, almost nothing. Unlike most mutations affecting bone, the LRP5 gain-of-function variant does not produce brittle, malformed, or painful bone. It just produces dense, structurally sound bone in greater quantity. There are some indications that affected individuals can have minor issues with bone overgrowth in places like the jaw or skull, but these are rarely serious enough to require intervention. The benefit is the closest thing to literal physical invulnerability on this list. Falls do not break things. Impacts do not crack things. The skeleton just holds. The rarity is extreme. Only a few dozen families with confirmed LRP5 gain-of-function mutations are described in the medical literature, making this one of the rarest documented superpowers in the human species. Congenital insensitivity to pain. People with congenital insensitivity to pain do not feel physical pain, not high pain tolerance, not tough, literally cannot register pain at all. The mutation usually involves the SCN9A gene, which codes for a sodium channel essential to transmitting pain signals from nerves to the brain. Without that channel functioning, the signal never arrives. The benefit, on paper, sounds like a superpower. You cannot be hurt the way ordinary people are hurt. No headaches, no toothaches, no muscle soreness, no agony from injuries. Surgical procedures require no anesthetic for the pain itself, only for the muscle relaxation. Pain, the most universal human experience, simply does not happen. The biological trade-off is the cruelest one on this list. Pain exists for a reason. It is the body's most basic warning system. People with this condition often die young, not because the mutation itself kills them, but because they do not notice broken bones, untreated infections, ruptured organs, or burns until the damage is catastrophic. Children with the condition routinely lose fingers, suffer untreated fractures, and develop joint destruction from walking on injuries that should have stopped them. The reason this is not ranked at the top of the list, despite being the most superhero-like condition, is that the real-world version is closer to a tragedy than an ability. The rarity is severe. Congenital insensitivity to pain is found in fewer than 1 in a million births, and the mutations responsible are recessive, requiring both parents to be carriers. CR5 delta 32. The CCR5 protein sits on the surface of certain immune cells and provides the doorway HIV uses to get inside them and replicate. Some people are born with a 32 base pair deletion in the CCR5 gene called CCR5 delta 32, which essentially removes the doorway entirely. HIV approaches their cells, finds no entry point, and cannot infect them. People homozygous for CCR5 delta 32 carrying 2 copies, are functionally immune to the most common strain of HIV. They can be exposed repeatedly and never seroconvert. The mutation has also shown protective effects against smallpox in historical studies, which is one of the theories for why it became common in European populations in the first place. Survivors of the plagues and pox outbreaks of the past disproportionately carried the variant and passed it on. The biological trade-off is small but real. CCR5 delta 32 carriers may be slightly more susceptible to certain other viral infections, including West Nile virus, because the protein the mutation disables also plays roles in immune signaling more broadly. You do not get to disable a useful biological component without losing some function somewhere. The benefit is genuine biological immunity to one of the most devastating pandemics in modern history. The rarity, by mutation standards, is modest. Around 1% of people of European descent are homozygous, and about 10% are heterozygous, the latter group carrying partial resistance to HIV infection even without full immunity. CETP mutation. The CETP gene affects how cholesterol moves through the bloodstream, and a specific variant of it has been quietly running the leaderboard for human longevity. Long-lived Ashkenazi Jewish families studied by researchers consistently turned out to carry this variant at much higher rates than the general population, and the centenarians among them showed dramatically reduced rates of cardiovascular disease, dementia, and metabolic decline. The mutation alters the ratio of HDL, or good cholesterol, to LDL in a way that protects the heart and brain over decades. The same effect can be partly reproduced with medication, but the carriers get the benefit baked in from birth, accumulating across an entire lifetime of cellular protection. The biological trade-off, as best researchers can tell, is essentially nothing measurable. Long-term studies have not found significant downsides, which is unusual for a mutation that produces such a large positive effect. The benefit is straightforward: a meaningfully higher chance of reaching 100 in good health with sharper cognition and a slower decline curve than the average person could ever hope for. The rarity is concentrated rather than dispersed. The variant exists across populations, but appears at notably higher rates in Ashkenazi Jewish communities and certain other isolated genetic groups, where founder effects have preserved it across generations. The fact that the longevity gene is the closing entry on this list is not a coincidence. Extending lifespan in good health is, biologically, one of the hardest things a mutation can do, and CETP carriers have one of the few naturally occurring keys to it. If you enjoyed this video and want to see more, click the video on the screen now.